So, good afternoon, everybody. I'm Jess Tsai, the chairman of this round. So, at first, let's introduce the jurors. So,
I'm Shin Dong from NTNU.
Hello everyone, I'm Lin Junyan from Suzhou University. I'm from the National Taiwan University.
okay. Yeah, so then please introduce your team member. From the board.
I'm Zheng Yongchen, we are from National Taiwan Senior High School. And this is Jin Wei, Zheng Daniel, and Jiawen. So, hello everyone. I'm the captain of Team GWP, and I'm Hong Yubo. Please, Hong Yubo. Show the one, please. Thank you.
Opponent.
Hello everyone, we're Team Maxwell from Kaohsiung Senior High School. I'm Cai Wengkai, and these are my teammates Wang Yanjun, Li Hongyong, and Hong Huanqian.
Okay. Yeah. So in the final round, it's a little bit different. Yeah. So because the questions you have chosen. So now let's start with 5 minutes of waiting. Okay. So please prepare. So please write down the name of the reporter, reviewer, opponent. Oh, okay. So let's start.
My name is Zheng Yongchen, and we are from National Taiwan Senior High School. And our team, today we are talking about our problem statement. Attaching a ball to each end of a string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the ball starts to climb and oscillate with increased amplitude. Investigate this dynamic. And our research question is, why does everything increase so? And this is our key concept. This is a hypothesis. First, the streamline motion of lateral follow the concept of force-stem oscillation, especially under oscillation of the pivot. Third, second, force-stem oscillation will contribute to make F2 of the most concrete. Yes. So we have 4 parts. This is first part, pendulum motion, where the angle from vertical line to the rope is less than 5 degrees. A whole motion can be considered through simple harmonic motion. So this is the formula. But the angle is usually greater than 5 degrees. So this formula needs to be corrected as this formula. And at those formula, the process does not include a moment which two balls kind each other. This is the second part, in ST collision. We design an experiment in order to realize whether lateral is ST or in ST collision, so that we can know this data loses energy or not. Next. Okay. So this is our setting. And according to a conversation of energy, the velocity of n1 before collision is rule number 2 times gravity times h. So after the collision, it is clear both that n2 cannot return to its original height. And this theorem is why we use checker to calculate it, and n2 cannot return to its original height. Therefore, the collision is in ST. Yes. So we use constant of restitution to mean the energy transfer during two those kind, and this is the formula. And we use checker to calculate it, and it is 0.863. And when E is bigger than 0 but smaller than 1, this motion is in ST collision. So regarding this information, we can use kicking energy to calculate the losing energy. This is our formula. Next. So force-stem oscillation. Force-stem oscillation refers a damped oscillation under the periodic external force. So this is our formula. Next. And after we use the formula to calculate x, and x can be this formula. And when this is a natural frequency, and our external frequency is very close to the natural frequency, and the F2 will increase suddenly. Yes. So our last part, energy transfer on the rope. When we realize two balls from 45 degrees, they climb continuously before losing their energy. So it doesn't show the phenomena that the F2 is increasing. Therefore, it is clear that the string through the oscillation of the pivot does work on the two balls, causing the F2 to increase gradually. Next. So this is our case. So, yes. Next. 0.1. So we decided to change the length of the rope. It is they are about 25 and 17 and 9 centimeters. And we change them to investigate the F2 of the two balls. Yes. So this is our figure, and x-axis is the time, and the y-axis is the position. And pivot is the y-axis when we shake, we use hand to shake the pivot. And N1 and N2 is the both horizontal location. And we calculate T from the pivot, and T is 0.39 seconds. And we use simple harmonic motion to measure the T0. And it is, we use 2 times time times root number length divide gravity. And we calculate it is 1.01 second. So as the pivot continues to oscillate vertically, the F2 of the two balls increase. Yes. So this time we change the length of the rope, and we also found that the F2 of the two balls is still increasing. So this time we also change the length of the rope, and it is 9.35 centimeters. And the T and T0 is also changed. So we found the F2 of the two balls is increased. So when we use data to find the connection between T0 and T1, we found that the reticle is about 0.4. So we designed an experiment about the Arduino's frequency. So we change frequency of oscillation to investigate the amplitude of the ball. So we define the length is 5.4 centimeter, and the Arduino, and the T is the period given by Arduino, and T zero is the period of pendulum with 30 degrees. And we found this formula, and in this formula, you can see a video. The video doesn't show the oscillation obviously. Next. And this time we change Arduino's pendulum to 0.3 second, and formula is just like that. And it still doesn't show the F2 oscillation obviously. So next. So this time we change Arduino's frequency to 0.2 second, and formula is just like that. So in this video, you can see an obvious vocation. Next. So I want to know why this formula when t equals to 0.4 times t0. So we use Python to simulate the motion of lato with different p. And this is when t is 0.85 times t0. It then shows the oscillation. Okay. And when t equals to 0.6 times t0, it doesn't show. Okay. But when t equals to 0.4 times t0, it has an obvious oscillation between two poles. So discussion. How does F2 increase? When two poles climb while the pivot is moving up, the tangent in the spring change. Although the tangent to do the work on the poles is giving the ball picking energy greater than the energy loss during the collision, cause the F2 to increase. This is our figure in the experiment. Yes. And why does the change in frequency will affect the motion of lato? The entire motion process includes external driving force, damping effects, and in ST collision. When the motion is similar to the fourth step oscillation, unlike ideal oscillation, the F2 does not reach its maximum immediately, but gradually increase over time. When the diving oscillation period approaches the system's natural oscillation period, the energy input from the external force compensates for the energy losses due to the collision of the damping. Eventually cause the F2 of the two balls to increase with progressive. And this is our figure. The x-axis is time, and the y-axis is speed. And when the velocity increase, the energy will decrease. Yes. So conclusion: just release the balls, and its F2 will reduce until the energy transform from the frequency losses, all due to inelastic collision and error resistance. And second, if certain periodic oscillation of pivot, the F2 will be increased over time, which t is about 0.4 times t0. When the tangent do the work on the ball, this gives balls kick energy greater than the energy losing from the collision, causing their F2 to increase. Last, therefore, the motion of lato can be considered a combination for both stem oscillation and ST collision. Thank you.
Well, first of all, thank you for the report. Now, could you turn to page 6? Okay, I'm sorry, page. So you mentioned the coefficient of restitution, right?
Yeah.
Okay, so can you show the video?
Thank you. Okay.
So you use the, and so you can you play that? Okay, so do you think that this situation is kind of different from what the collision is when you're playing lato? Do you think it's the same?
Yes, I think it's the same because we only want to calculate the consequence of.
Okay, thank you. So can you turn to page 9? Okay, so so what is the natural frequency? What do you mean by the natural frequency of the lato-lato?
I think the natural frequency combines a lot of elements, just like the quantum oscillation
Okay,
and.
can you turn to page 11? So in your steps, you wrote that you're using your hand to control the pivot.
Yeah.
So did you consider that the frequency of your hand might change?
Yes, we consider,
Turn
but
to page 18. Yeah, thank you very much. 18, sorry. Can you play the video? So as you can, I think we can clearly see that the lato-lato is moving in 3D motion. So did you consider that in your theory?
oh no, because
Some questions. Okay, hello everyone. I'm the opponent from Team Maxwell, and today I'm going to be opposing problem number 3, lato-lato. Okay, so this is the problem statement. We have to attach a ball to each end of a string, and we have to oscillate the pivot at the center of the string. And when the pivot oscillates, the ball will start to collide and oscillate with increasing amplitude. And we have to investigate this phenomenon. So the key points that the reporter mentioned were the comparisons with a simple pendulum motion, and the reporter also mentioned force-damped oscillation and how it was important, and how the amplitude increased, and the importance of it being an elastic collision. So first, about the summary of the report, the reporter first considered a simple pendulum and then fixed the theory to account for higher angles of the pendulum, and also considered that the collision was inelastic, and also calculated the coefficient of restitution. The reporter also managed to use the parametric oscillation to describe this phenomenon. As for the experiment, the reporter used the hand to control the lateral, and from the presentation it seems that the reporter also managed to try to use an Arduino motor to control the lateral in certain experiments. And for the parameters, the reporter changed the rope length and the frequency of the oscillation. So the reporter found that when the frequency was at a certain range, the oscillation amplitude would start to increase. And that the system can be regarded as a force-damped oscillation system. And onto the strengthened suggestions of the report, first I think the reporter gave a somewhat clear qualitative explanation of how the lateral increased its amplitude during the oscillation of the pivot. So the reporter used some energy perspective about how kinetic energy was given to the ball to describe why the amplitude increased. And also I would like to commend the reporter about providing some quantitative theory and attempting to describe this phenomenon using their quantitative theory. For example, about the natural frequency and the force-damped oscillation. And also, I think it's great that the reporter managed to use some simulations and compare their simulations with real-world experimental results, and managed to find that the results were pretty similar, which is very good. However, onto the suggestions, first of all, I think there could be slightly more explanation as to how the energy was transferred into the pulse and why the amplitude increased, because I think that's a very important part of this problem statement. And also, I think there should be a little bit more explanation on when the amplitude will increase. For example, the reporter did consider the frequency of the oscillation. However, I think perhaps, for example, the amplitude of the oscillation of the pivot will also affect this phenomenon. Next, the reporter managed to use a motor for some of their experiments. Some of the experiments were conducted by hand, which I think could be improved slightly. As using their hand will cause the lateral to not be in a 2D sort of motion, and perhaps some aspects like the frequency of the oscillation would also change. And I think that there could also be slightly more explanation about the damping and why it is important. And the main source of the damping, which the reporter could also explain a bit clearly. And finally, as I mentioned, there were some videos about lateral swinging actually in the 3D dimension, which the reporter did not cover, and that's all. Thank you. Now, I would like to invite the reporter for the discussion. Okay, so first of all, I want to talk about why the amplitude increases.
Why the amplitude increases?
I kind of, well, yeah, I'm very curious.
It is greater than the energy using during the condensate, so causing the amplitude to increase.
Do you think that using your, for example, your hand to move the pivot will give the ball kinetic energy?
Yeah.
And so, how does this kinetic energy transfer into the height of the ball?
So can I use?
Sure.
Use that. Actually, the chance of the pendulum, the PB up and down, and the PB is down, and the strap will loosen. Do you agree?
Yes.
So when the strength is loosened, the pendulum will smaller than the PB is up. Yeah. So when the when our PB is down, our pendulum is smaller. So we can use. So the toroidal is more than the output. So the potential energy will
So about the increasing amplitude. So what do you think are the very important factors in terms of the oscillation of the pivot? For example, in your report, you did talk about the frequency. So do you think that there are any other factors in terms of the oscillation of the pivot?
Can you repeat again?
Okay, sorry. So you mentioned that the frequency is important, right?
Yeah.
So do you think there are any other important parameters?
I think maybe it's just like force demonstration, but because it is a charged system, so we can actually design what character will.
You mentioned that it was chaotic.
Can you explain what it is?
What you said it was okay. I think you said it was chaotic, but never mind. So I think that you also mentioned that the main focus for force depth oscillation is going to be the frequency, right?
Yeah, but it actually does force depth oscillation because okay. In force depth oscillation, we think that the oscillation will certainly be a maximum, but in orthogonal motion, it doesn't. It gradually lead to maximum.
Okay, I think we'll also discuss that later. But I think that there are also other important factors in the oscillation of the pivot that will affect the increasing amplitude. For example, if the oscillation is very small, even if the frequency is even if the frequency is close to what you mentioned, maybe 0.4 times the natural frequency, perhaps the oscillator would not be able to increase its amplitude.
I have shown before. Just because the tangent. And you can see this video. The input is sometimes decreased and increased.
Can you explain why that happens?
So just like a tangent. The tangent it depends on what the pivot is up and down. So the tangent will affect the amplitude.
What do you mean tangent? Oh, okay, I got it. Thank you very much. And also, perhaps the phase would be quite important as well. So, like when you choose when you move the pivot up and when you move the pivot down, I think that's also a very important factor. Would you agree?
Yeah.
Yes. Next, I want to talk about. Can you turn to page 7?
Time is up. Just discussion. Yeah, sorry. So what's the time? Okay. Yeah.
Okay, can you show the, so you use the height to calculate coefficient, is that correct?
Yeah.
Also, so you're using the, okay, never mind. Can you play the video about this experiment?
I doesn't use this experiment because I think the calculation
Yeah, I think you had a video, right?
So what do you want to know about?
Like you had a video about releasing a ball.
Oh.
About, yeah, I want to share. Okay, thank you very much. So, can you play a video? So first of all, do you think that the coefficient of restitution is the same?
Yeah.
Okay. I will agree. And so, do you think using this way to calculate it would perhaps maybe be different because I think that when the lato is being played, they actually meet at the middle, and like the two balls are actually always at the same height.
But in this motion, we just only calculate the comparison of the resolution. We don't if the motion of lato can be thus described. I think it is not important. I think it's not.
Okay, and maybe perhaps it could also be in your future work about this motion, and perhaps you could maybe this will lead to different results. If you maybe release the balls from the two sides and just let them drop, maybe I think maybe the
No. We have design a meeting, and we have used 90 degrees. But
yes, but what I'm saying is that maybe you can release the balls from here and just
but in that video, the rope is not straight. Yeah, it will transform into some like crown shape because our hand is not I think our hand is horizontal velocity, so hand the shape drop.
Okay. Okay. Thank you. We'll also move on to the next part. So, can you turn to like you mentioned the importance of the natural frequency as about page 9. Can you go to that page? Yes. So, okay. I think we'll go to your experiments because maybe it will be clearer. Like the experiments about the frequency of the oscillation. Yes, like you changed the frequency. Okay, thank you. Okay, first of all, you mentioned that the lato will actually increase when, for example, the t is about 0.42, right?
Yeah.
And so, why is it?
Oh, because we think we actually don't know, but in our experiments, we only do this experiment and we found that. So we don't know what. So we use Python to simulate the different.
Okay, thank you. So, as I mentioned, frequency is very important for stem oscillation. So perhaps you could also try to investigate it from your perspective. And also, as you can see in the video, the lato is not actually moving in 2D, correct?
Yes, because checker only can use 2D, so we decided to use 2D to describe this motion.
Okay, so perhaps you could also try to limit the motion to 2D. Maybe that will have some different results. And finally, I want to talk about why the amplitude stopped increasing in your video.
So time is up.
Okay.
Opponent, please summarize.
Okay, so for my summary of my discussion with the reporter, first of all, we discussed the mechanism behind the lato and why the amplitude was increased. So the reporter thinks that the frequency is very important. And in our discussion, we also agreed that perhaps the amplitude of the oscillation and maybe when you do the oscillation would also be quite important. So if the value, for example, is not enough, maybe it will not increase. And we also discussed how the reporter calculated the coefficient of restitution, and the reporter also did a lot of experiments trying to calculate this coefficient of restitution, and I suggested that maybe a way of calculating it more similar to how the lato is played might lead different results. And so we also talked about considering the 3D motion, and that's all my summary. Thank you.
So the question time for the
This question is for both the reporter and the opponent. So what makes the lato collide initially?
I think the energy change.
Energy change. Okay, what do you think?
Okay, so I would probably just put it down, and I also agree with the reporter that the energy
Okay.
change.
So on the reporter, have you connect any experimental data to theoretical data? Because I see that you've done a simulation in VPython, is that what you said?
Yep.
Yeah. Have you done like comparison for the statistics between experimental data and theoretical data?
No, because we only found one, two.
Okay, thank you. So the next question is for both the reporter and the opponent. So does the tension force do work when the pivot goes up, down, or both? Let's start with the opponent.
I think it kind of just work when it's going up.
Okay, then what do you think?
Can you repeat again?
Does the tension force do work when the pivot go up, down, or both?
Both.
Okay, do you want to elaborate on your answer?
When the pivot is down, you do the positive work, and when the pivot goes down, you do the negative work.
Okay. In our opinion, we also agree with the reporter that when the pivot goes up, it does positive work, and when it goes down, it does negative work. So how do you control the initial angle? Yeah.
We didn't control the initial angle.
So without the initial angle, how does Lagdato start oscillating?
Okay. Yeah. We only cause just like.
So there is an initial angle.
Yeah.
Okay. So what is the initial angle? What is the initial angle?
What is initial?
Initial, like the beginning. Before.
Maybe 0 to less than 5.
Okay. Then do you think there should be an initial angle?
I think even if there is an initial angle, the initial downward movement will cause a small angle.
Okay. Then how do you control the frequency of pan? Because there's several experiments that I saw that.
We only choose when we control the loss alone. But if you want to change the control frequency, we use the VPython.
Okay, thank you. Do you acknowledge that when measuring the coefficient E in the experiment, you said you use the tracker and it's the value of 0.863?
Yeah.
Do you acknowledge that when you're tracking the E, damping is also considered inside?
Yeah. So.
Then wait, it doesn't make sense because E is a discontinuous constant. However, damping is a consistent motion, so you cannot value E when there's damping inside. Okay. Next to the next question. You mentioned about chaotic motion, right? So are there any mathematical proof that proves it's chaotic motion?
Motion?
Okay. To the opponent, have you considered slack or vibrate? Do you think the opponent
time is up.
Judges, opponents, fellow contestants, and fellow debaters. This is the review from Team GGWP reviewing the topic number 3, Lotto Lotto. Let's start with the problem statement. The reporter focuses on simple pendulum moments, force damped oscillation and elastic collision, and work done by the various tensions. And as for summary of the report, the phenomenon is when the ball collides in an increasing amplitude, or the pivot undergoes a vertical motion. And the theory that the reporter introduces are an elastic collision, restitution coefficient, and there will be a more complex when the angle is above 5 degrees. The variables are the length of the rope and the frequency of oscillation. As for the pros and cons for the reporter. So the preliminary experiment of coefficient of restitution is pretty well done, and then there's a pretty complete report outline, and uses Arduino as a motor to conduct the entire experiment lotto. And so, however, there are still some cons that we may suggest you guys. So the first one is unclear theory deviation, and there's no reference on page 9 because I see that there's an URL that does not connect to a reference, which we believe as very disrespectful to the author. The next one is the simulation spring is always taught contradictory to the reality. As for the opponent had a complete discussion of the reporter and considered 3D motion, which we believe as a really important factor as well. However, there are still some cons. For example, you should also consider string vibration and slack impact in the system as we see in the observation video. For the discussion, the opponent asks why the amplitude increases, and the reporter responds with kinetic energy is greater than the energy loss, causing the amplitude to increase. And the opponent asks why do you consider 2D motion, and should the limit of lotto to be 2D motion? And the reporter responds with tracker can only track 2D motion. In our opinion, we agree with the reporter, but you need to provide a condition that will satisfy the pseudo 2D motion. There needs to be a broader explanation for this. For the discussion, the opponent asks what if you release the ball at the different places, and the reporter responds with hand exert different forces. Next one is about lotto increase at 0.42t. And then the next one is when I ask what makes a lotto collide initially, and then the reporter responds with energy change, and the opponent agrees with the reporter. Next, I asked, have you done a comparison between the theoretical and the experimental data of the experiment? And the reporter did not do it. And then I asked, how do you control the initial angle? And the reporter says they did not control the angle. The next one is, I asked them about the elastic coefficient experiment, and then damping is included, and the reporter replies that there's no problem with it. There are some missing points that I would like to elaborate on for both the opponent and the reporter. First one is motion equilibrium, and next one is energy loss from vibration and slack, as we have observed from the reporter's video. Next is the reporter lacks quantitative results, which we believe will definitely benefit your future researchers. The next one is you have mentioned about chaos and the chaotic movement of the lotto, but you need to provide a more thorough mathematical provement in order to say this. And the next one is we observed from your video on power slide 23 that there's a coupling effect, which you failed to elaborate on. The last point is the fact that playing the lotto in reality, actually we wanted to collide at the semicircle above, and however both the opponent and the reporter failed to acknowledge this. And we think that not only frequency will let the lotto increase amplitude, but also the length and amplitude of the oscillator effect. That is the end of the review. Thank you.
So concluding remark.
Within that, the movement of pivot is important, and natural frequency is important too. And knowing that when t equals to 0.4 times t0, the oscillation will increase from its zero. And we have have a discussion about the tangent. And yes, return to the review. Yes, we control the angle, and it is less than 5 degrees. And I think the constant of restitution is only above the last. And return to the review, and childlike motion, I think it is the motion of lotto is this system. That's all.
So the question time from the jury. Yeah, so Professor Bai.
When you increase this pivot oscillation frequency, you will see just a single resonance, or you will see a multiple resonance.
Can you repeat the question?
If you increase the frequency of this pivot vertical oscillation, will you see this single resonance or multiple resonance?
We see multiple resonances.
Maybe in the external.
Yes.
Yeah. Okay.
We feel it's the ratio between natural frequency and the frequency of the Laplace.
And the reporter had this observation of this t equals 44, t0, right?
Okay.
So that's way off from the multiple of the relational frequency. So why is that? Okay.
So for the proponents, do you want to answer?
I don't know. Just,
Okay. So is there any? Yeah. So
I
Professor
have
Bai.
a question regarding the rope, string, or thread, whatever you want to call it. So does the material making up that string, rope, whatever, with how does that material property affect your experimental results?
I think we can reach our constant of restitution resistance and about
Material of making up the rope,
Oh, rope.
not the ball, right?
It's about the same. And it is sometimes it is the negative work on the ball.
Of you.
Mag is a blackboard.
Yeah.
Okay. So if it's a stick base, if it's long lateral, right? So if it's a stick base, it'll have like a circular motion back. However, if it's a string, it'll perfectly come back down.
And reporter with the reviewer, so if the rope, for example, is harder, then as the reviewer mentioned, it will be a bit easier for to actually complete a full circle. And also, elasticity of the string might also affect this fundamental.
So Professor Kang, and also please specify who you want to ask. So Professor Kang.
I would like to ask the reviewer. You mentioned the so-called slack impact. Could you elaborate? What do you mean?
So when we're playing the la in reality, right? So we actually want to make it so that it moves upwards, right? So if there's slack, if the balls goes above the horizontal surface of the pivot, there's actually will be a slacking effect that will push it down.
You mean the rope itself is not tightened?
Yeah, because it
Okay.
moves above the
And
horizontal.
what kind of effect that it will cause?
As we mentioned, it will cause energy loss similar to vibration.
Do you agree with the reviewer?
Yes.
When the slack occurs?
So when it's like turning upward, I think that the lateral will usually be moving fast enough in a successful like playing of the lateral that the string will be tight.
Okay, so is there some further question? No, let's go on. Okay. The score for the reporter. Six, 5, 6, 6, 5. The score for the opponent. 7, 6, 8, 7, 6. The score for the reviewer. 8, 5, 8, 6, 7. Yeah, so I think that the score are quite consistent. So, is there any, talk with the student?
I have a suggestion. The opponent, in the beginning, you asked several questions to the reporter, but you didn't give him a chance to answer. I think that's a bad manner.
Okay. So let's conclude this session. Yeah.